tanto en Zoom como los que están aquí presentes. Hoy comenzamos el tercer día del primer Congreso Internacional de Inteligencia Artificial. Les agradezco a todos los que están aquí presentes físicamente y también los que están presentes a distancia por Zoom. También agradezco a los ponentes que están aquí participando en esta conferencia. Entonces, como ya sabrán, pues esta primera plática será por Giorgio Metta. La presentará en inglés, entonces creo que voy a tornar a hablar en inglés. Entonces, we start. This talk is called Building Components of Human-Robot Interaction on the iCub Humanoid Robot, and is presented by Dr. Giorgio Metta. Giorgio Metta is the scientific director of the Italian Institute of Technology, IIT. He holds a master's degree with honors in 1994 and a PhD in 2000 in electrical engineering from the University of Genoa. From 2001 to 2002, he was a postdoctoral associate at the prestigious AA Lab at the Massachusetts Institute of Technology, MIT. He worked at the University of Genoa and was professor of cognitive robotics at the University of Plymouth. From 2012 to 2019, since 2020, he has been visiting professor of the University of Manchester. He managed the relationships with funding bodies and international relations on behalf of IIT. And in this role, he was a member of the board of directors of Euro Robotics ISBL, the umbrella association for European robotics. Giorgio Metta served as deputy scientific director of board of directors of deputy scientific director of IIT from 2016 to 2019. He has coordinated participation in two of the Ministry of Economic Development Competence Centers of Industry 4.0, ARTES 4.0, STAR 4.0, for which he has served as a member of the board of directors and the executive board, respectively. Until October 2023, he was one of the three Italian representatives at the 2018 G7 Forum of Artificial Intelligence, and more recently, one of the authors of the Italian Strategic Agenda of Artificial Intelligence. He is a member of the governing board of Digital Innovation Hub Liguria, of the Scientific Council of Human Technology Lab of the Catholic University, scientific advisor of A-Star Singapore, a member of the BOD of Rise Skull, a project funded by PNRR, of the Executive Board for Digital Next Generation of the Liguria region, of the Scientific Technological Board of RINA SPA, and won the BOD of Jeffran SPA and the Board Directors of Industry de Nora SPA. Giorgio Metta's research activities are in the field of bio-inspired systems and humanoid robotics, with a focus on the design of machines that can learn from experience. He has co-authored more than 300 scientific publications and worked as a PI on about a dozen of international and industrial research projects. He has coordinated the development of the iCub robot for more than a decade, making it a de facto platform of choice for research in AI. There are currently more than 50 robots in the world in research labs as far as Japan, China, Singapore, Germany, Spain, the UK, and the USA. Then please start. Thank you. Thank you for being here.
Thank you. Can you hear me? Okay. I'll move quickly, to the slides. And in fact, just reconnect to what you were saying. And thank you for the kind of introduction, by the way. I wanted to go through a bit of the history of the project, a project of human robotics that, in fact, was born thanks to European funding back in 2004. And then, since I'm not doing research myself anymore, or not firsthand for sure, I'll be presenting two components of the research that is currently carried out at IIT on the iCub human robot. So this is roughly what I would like to say. So first of all, where we started this, you may recognize this as a photo from a Hollywood movie that sort of goes after the bicentennial man of Asimov. That's the story. I decided to take this story because I think it represents well what we like to do with humanoids, and also it's one of the few positive movies. most of the movies end up in disaster, and the reason is that you need a bit of action. This one is more on the calm side and presents two phases of human robotics. One is the ability to interact with a human robot like you will interact with the person, and the other one is the ability, like in this case, of the robot do something for us where we may be not strong enough for doing it, like in this case, carrying weights. As I said, we decided to design human robots, and we needed the money to do it. So what we applied for, I was just finishing my postdoc at that time, was European funding. In one of the first cases where Europe funded large enough projects. So we received about 8.5 million euros to actually run the project, design the robots. It was collaborative effort across Europe. These are the partners. We work with other people in Italy, but also in Switzerland, in Sweden, the UK, Portugal, and there were also companies involved that helped us with designing the mechanics, the electronics that was needed for having something of good quality, good enough quality to be used in a research lab and break not too often. It breaks still. It's not an industrial robot, but was well done enough to be able to support our research. This is what we ended up designing. It's a robot it's about 1 meter tall. It's shaped as a, 5-year-old child, roughly. The reason is that this was one of the few robots that we can keep in a standard laboratory. You don't need much support because it's not too dangerous. I mean, it's still heavy enough, but you don't want it to follow your feet. But normally you can work with a robot like this one. The other thing is that you can see from the picture to the right, it's a robot covered with tactile sensing, so tactile sensors. So there are about 4,000 sensing points across the robot body. I think there are not that many machines of that type, even to date. Touch is kind of underestimated. Sometimes robots have fingertips that are sensorized, maybe the hands are sensorized, but the entire body is very rare. And this is something it required another project and further development to actually design the sensors, but ended up providing some additional capability to the robot. Also, we like to call it, you see the Ferrari logo down there, has nothing to do with Ferrari, but we sort of consider this platform, this robot, as a Formula One car. Not because it's extremely fast in this case, but because it runs for the time of a Grand Prix, and then you have to replace the engine in the case of the car. And here, you probably had to replace tendons, you have to replace components. So there's a lot of maintenance work that is connected with using the platform. Couple of design things. We started with hands as in a sense, the most difficult component to design mechanically. We wanted a hand with articulated gestures, a hand that could do, for instance, pinch grip or power grasp. So 5 fingers, enough degrees of freedom. And this constrained, in a sense, the design of the entire robot. I mean, a hand with 9 motors, you cannot put the motors in the hand. So we had to move the motors into the forearm, which means you need tendon-driven fingers. And this constraints also further where you place the other motors. And the entire design is sort of constrained or conditioned by the fact we want to sophisticate hands. In terms of sensors, we were very strict at that time. So first of all, 3D cameras didn't exist in those days. So what we used was standard cameras, wanted to be able to do stereo vision. We had moving eyes, which I think is a feature that you don't see very often in human robots these days. They're typically fixed. Here, we wanted to be able also to gesture by looking in certain directions, and we see later this is an important feature. We don't have Everything else is tactile. I mentioned we have microphones, we have gyroscopes and accelerometers to sort of provide a sense of the body posture. We have 4-star sensors that give feedback on the contact of the robot with the ground, with the environment in general, besides the tactile sensing. And last but not least, we made open source. So even to date, the drawings and the software is available for download from our website. I mean, it's not perfect because, of course, we are a research institute. We can't provide complete support, but it was good enough to have other researchers kind of jump in with developing for the iCub. And we eventually, I think, managed to create, at least for a certain number of years, a large enough community of developers that were working with us. This was an example video showing the hand of the robot. This is another, let's say, structure of sensors on the robot design, showing roughly where the sensors are mounted and giving an idea how relatively complicated it was to put so many connections, so many sensors on the robot body. And this is eventually, if it starts, it's a video that shows zero gravity control on the robot and the ability to basically keep the robot there, push the robot very gently, and the robot will keep moving just because it senses pressure, it senses the force that the person is applying to the robot. I think the video is old enough that it doesn't play on all computers. And I mentioned the fact that we had, or we still have, a community of users of the iCub, and end of last year we had more than 50 robots across the world. I don't know how many of those are still used, because people tend to use the robot for a while, because maybe there was, at least for the European robots, there was funding, there was support from European Commission projects, but I know for sure that some of the robots are not used. But anyway, it all contributed in a sense to building experiments, building or designing or programming more behaviors on the robots and so forth. So it was a nice adventure. But let me tell you something newer. So this was history. What are we doing to date at the Italian Institute of Technology, more specifically? What you see here is one component of the research, and in particular is the component that studies social human-robot interaction, where most of the interest here is not on the robot, but it's on the human. Of course, you need a robot because the robot is being programmed to interact in certain ways with people. But here, what you can see is the typical setup in cognitive neuroscience, where we have a gaze tracker in the glasses, we have an EEG to record brain activity, there's a keyboard exemplifying the fact that we can measure reaction times, for instance, or other behavioral, let's say, we can collect behavioral measures that then can be used to clarify what's happening during the experiments and so forth. And the robot is fully interactive, also because these days it's very easy to have, for instance, a robot finding your face, looking at your eyes, being relatively autonomous in the interaction with a person. I'd like to start with a very basic experiment, which is mutated in a sense on something called poser queuing. This is a very standard cognitive neuroscience experiment, and the original goes this way. You basically have a cue, which is an arrow that tells you, in a sense, where to look, and then you have a stimulus that can appear either congruent with the arrow or opposite, incongruent with the arrow. So let's say the trial on top is called a valid trial. This other one is called invalid. What we said, why don't we, in fact, replace the arrow with a human robot? I mean, it's easy to do. And also, in that case, we can manipulate the context because we can have the robot looking at you, or you can have the robot avoiding gaze. So the configuration of the experiment can be changed in various ways. This is a video showing how the experiment goes. You see valid Q is when the robot looks in one direction and the letter appears in that direction. There's eye contact here. So the robot looks at you. You can imagine the subject sitting in front of the robot. The other case, without eye contact, the robot looks at the table, in a sense, kind of avoids gaze, and otherwise the experiment goes as previously. Robot looks at one of the screens, and subsequently the stimulus appear. Okay, results. What we've done, like here is reaction times, for instance, is one of the measures that we can use. And what happens? Well, something interesting, because in the case of eye contact, like you can see here, there's a difference between the two conditions. The two conditions are valid and invalid. So you faster when the robot is cueing you to look in a certain direction. And in fact, the stimulus appears in that direction. So you're faster in saying, okay, I saw that. When there's no eye contact, in a sense, you're more distracted, maybe. There's no significant effect in the valid versus invalid condition. So this seems a nice story, and we thought, oh, maybe we found something. We tried manipulating a bit the timing of the moment the robot starts a movement and the moment the stimulus appears. This is called SOA. And in fact, what happens is the situation is completely changed. The two conditions have no difference. There's always a validity effect, both when the robot is looking at you and when the robot is not looking at you. Now, the question is, or the take-home lesson of this experiment is that this little change in timing actually modifies the perception, your perception of the robot as an interaction partner versus something that has a completely awkward timing, and therefore it's no longer an interaction a partner. And this is important, because if we're designing robots to be social one day, we may need to actually know when to start a movement. It's not random. It cannot be random, because otherwise we don't perceive the robot accurately as an interaction partner. Just as a summary of the experiment, well, there's an effect. So joint attention with a robot has an effect on the way we perceive the robot. And also that the robot gaze indeed is treated as a social signal. I mean, this wasn't necessarily to be the case. It was an empirical question. We asked the question, we ran the experiment, and we found that this is the case. I'm more, in a sense, I'm more interested in the question of the timing, because as an engineer, when designing a robot, I would like to understand when to do certain things. And the fact that I need to write a piece of software that decides when to do a certain movement is utterly important for how we perceive the robot. Another experiment along similar lines. In this case, there's a little video game that you play on a table. The table is a screen. In fact, there are two cars going one against the other. You can take a decision to deviate from the straight trajectory and therefore avoid crashing, or you can keep going and count on the robot maybe deviating. So of course, there's the robot has a strategy. There's a payoff matrix, so you get points when you don't crash. If you go straight, you get more points if you don't crash. In case of a crash, both you and the robot lose points. In case both deviate, which means you're not even trying, you get a small number of points. Now, the game is you have to try to win against the robot. And the robot can look at you again. So even in this case, there's a possibility that the robot is social in a sense. It looks at you, or antisocial, it's a bit shy and doesn't look at you. Here, the video shows exactly how the experiment is done. The robot actually presses the button to deviate. It does all the, of course, it's not strictly speaking needed, but this is makes completely realistic, and you play the game for a long time. Now, what happens? Well, there are interesting aspects also here. Also, in this case, is reaction time, response time, and you can see that first of all, there's no difference from when the robot is on average more social versus the robot less social. So there's always an effect because the two colors are indeed different. But so it doesn't depend on the personality, so to speak, of the robot. So a robot that is more social doesn't change the effect. But when there's mutual gaze, indeed you're slower than the case when there's no mutual gaze. So a robot that is antisocial is better for you and you faster in responding. There's also a way to check that on the EEG. I mean, the way it works with EEG is that you do the measurements, then you go into looking across the literature to see whether differences, like in this case, during the task executions are correlated with activation in areas that have been related or already connected with certain effects. In this case, there's particular zone that you see in blue there, which is known to be related to the necessity to suppress the stimulus. In this case, we hypothesize is the robot that having to process the information that is coming from the robot. And there's also, I mean, this is identified with this higher synchronization during the mutual gaze in a certain frequency band of the EEG signal from a certain electrode that is placed roughly in the blue area that you see there. So there's confirmation in a sense that your brain has to spend some energy, some effort in processing this signal that is coming from the robot. Another test on the same experiment, this is even more interesting, I think, is the following. So if you have the robot that is not looking at you, so the averted one, this brownish bar here, look at the most down plot. So the one that is exchanging gaze with you more often, the blue one, makes a smaller value of what? Of the time you spend on the optimal strategy. So you don't know the optimal strategy, but playing long enough, you start to learn something about the robot, and you start to use more and more the optimal strategy, which is called win, stay, lose, shift. So whenever you win, you keep playing the same action. Whenever you lose, you change action. So you press or not press the button. So what it means this is that if it's better to have a robot that doesn't look at you, maybe indeed the robot is a distractor. And therefore the take-home message is, if we designing robots for efficiency, maybe we don't want a social robot at all. I mean, it's much better to have a robot that doesn't distract you so you can focus on your task, which seems to be the case from this experiment. I think, again, this is another hint that for designers of industrial robots, maybe in the future, they can say, okay, if I go for efficiency and not for collaboration, maybe it's better not to have social signals. If I go for collaboration because the task requires collaboration, then I may need also the social signals. This is basically a summary of what we found with this experiment. So the robot can be distracting, in fact, and the delay and we're distracted, but also the delay is correlated to the necessity of suppressing an extra stimulus that is the robot looking at you. Let me move to more of an application topic out of this research. So this is the same group that is working on programming the robot for interaction. We had the opportunity to work with kids diagnosed with ASD. And this is, we thought of using the robot because, at least in the literature, there were a few examples where there were hints that this may be helpful. And in particular, to train kids that are diagnosed with ASD across battery of experiments and train them to behave correctly in certain conditions, in certain interaction scenarios. In particular, we ran a first experiment with a toy robot of that shape, a toy car, basically, remote controlled, can be programmed to behave in various ways and showing certain emotions, doing certain things. And we had positive results. So it's not very important now that I go through the result here, just to give an idea that even with a simple robot, there are hints that certain things may be paying off, but it wasn't as good as later with the iCub. So eventually what we did was to prepare a full-blown experiment. We brought the robot to sort of a school, an institute where the kids get teaching, they have normal sessions with physiotherapists, but also they had the opportunity to play with the robot for a certain number of hours. And this is the how the experiment was set up. You see that we needed a glass or a plastic, a plexiglass wall from separating the kids from the robot. This is for safety reasons. I mean, the robot is not certified. We cannot have it interact with kids. Very, very dangerous in that case. And this is a video that shows some of the experiments, what the robot does. Basically, what we were training kids to do was perspective taking, and this first experiment. The cubes have different faces with different sides with different stickers. The stickers, you can build a game where you're basically asking the kid to tell you what the robot is perceiving, what is the point of view of the robot. So in a sense, putting himself or herself in the robot's shoes and trying to get feedback from the interaction with the robot. So the robot can do yes, all good, or say no, it was wrong, and so forth. So this is the result. The test that you see here is the clinical battery of tests that is called NEPC2. It's normally used in clinics for assessing performance in certain tasks like geometric puzzles, but also theory of mind. And theory of mind is exactly perspective taking. And this is exactly what we wanted to measure and to see whether there's improve in performance over time after the kids play for several months with the iCub. Besides, they were all super excited to be playing with the human robot. Needless to say, this is also part of the therapy, probably. Okay, now results. Here we divided the kids into groups and have, so G1 and G2, both groups were going through the training but at different time. So we can actually measure whether after one run, there was improvement and we had a control automatically because the second group wasn't being trained, and we could check whether there was any change in the second group, which you can see here. So group one, the brown plot has improved in the theory of mind test because of the interaction with the robot, and the group two that did not interact with the robot, no change. And you can see also that after a time T2, we swapped the groups. So the group two at this point was interacting with the robot and being trained and going through the training. And in fact, there's an increase in performance. Importantly, group one didn't lose the capacity or didn't, the learning did stay. The other one on the right is interesting because it's a robot versus therapist, and it basically shows that the training works with the robot better than with a human therapist. And now the thing is, I mean, anecdotally, we can say that the robot is more fun. The robot is simpler. It's not like a person. It's easier to interact with for a kid with ASD. And this may indeed be the case. And also the robot is more repeatable. I mean, it does the same stuff every single time. So it's a lot more predictable for the kids. So this is, again, summary. So nice to have a robot to interact with the kids. And this is now is turning into a larger program because we're still working with this institute, and there's an opportunity for all their kids to teach them to be autonomous. So there's, I mean, the numbers are frightening. There are a lot of kids that lack the basic ability to go around, to be autonomous, to carry out daily tasks. And there's a chance maybe through technology to actually teach them to reach a level of proficiency that will make them more autonomous. Let me move completely to a different topic now. I mean, we saw the social human-robot interaction. Let's move to the physical human-robot interaction. Physical, not to be understood as fighting the robots. This is more just exchanging forces and interacting with the robot. This is the first video just to show you some of the capacity of the robot. Of course, when we talk about physical interaction, we had to be able to do things like this one. So the robot is force controlled, and it measures interactions through tactile sensors and the force torque sensors that I mentioned earlier. And therefore, you can push it around, and the robot is reactive enough and can balance, like in this case. Now, details. The robot runs a multi-layer controller. The lowest level, it's a QP optimal controller that integrates all the data coming from the sensors and generating control according to a low-level task. There are two more layers. One that uses an approximate model for giving the robot the ability to balance and walk. And then there is yet another model, even simpler, that does the foot placement. So the robot decides where to put the feet at every cycle. And again, the three layers are integrated one after the other. So the foot placement is commanding the balancing controller and the walking controller, which is commanding the QP controller that eventually commands each single motor of the robot controller. Now, in these experiments, we also decided to gather more information from humans, and I'll get to that in a moment, why this may be useful. And therefore, we designed a sensorized suit to measure roughly kinematics of the person. And additionally, we designed a pair of sensorized shoes to measure forces, exchange of forces with the ground. Therefore, we can use that measurement also to at least square calculate what may be the stresses on the various joints of the person. This is an example of how it works. And I mean, I think it does a decent job, both let's say the sensorized suit, but also the shoes. I'll show you in a moment a better representation that includes the shoes. Indeed, the shoes, by the way, they have force torque sensors, IMUs, temperature sensors, and they're completely wireless. So that's a added value that you can just wear them and you get the numbers. And this is a video where one of our students is playing with devices, lifting weights, and you see that there's a measurement of forces, but there's also measurements of the muscle articular stresses at the joints. This is useful in a context of a project that we received funding for, and this project was to actually try to estimate on one hand, what happens when you're carrying out certain tasks, what are the stresses? On the other hand, how the robot can help, in a sense, optimally to remove those stresses to your muscles. Motivation, 70% of injuries in work life are not because you do something completely dangerous, but just because you lift weights continuously. Sooner or later, over 25 years, those lifting weights causes articulatory problems, and people, at least in Italy, they file for insurance claims, and the insurance claims it's a lot of money, and therefore that's why they would like to have robots helping out in these cases. Now, with those sensors, there's more that can be done. This and this is useful. Again, if you're going to interact with a robot, you can train. This was a set of neural networks acting as a sort of a mixture of experts detecting or identifying different behaviors. And this came, again, as one of the components that is used in the system to figure out what a person is doing and deciding how to control the robot correspondingly. Now, since I said, okay, let's work with the robot, this is an example. It's difficult to perceive the quality, but I mean, the person is not making any effort. It's just touching the robot and lifting a little bit, and the robot knows the stresses, the articulatory stresses on the person, and therefore the robot itself is doing or finalizing the movement properly. This is another case where, of course, you can interpose an object like a box with a certain weight between the robot and the person. And again, you can build a controller on the robot that takes into account the fact that you have a way to be lifted, what is the optimal controller for the person to minimize articulatory stresses. I'm not entering into the details of this experiment because I must say the complication of the controller is fairly high here. Because there's this continuous exchange of forces, but basically we model the person like a robot. We have the complete model, and we model the dynamics of the object where the forces are exchanged, and then we try to optimize the entire thing, which is complicated, but entirely feasible in real time, as the robot is, you can see, is moving in real time. We also made it in such a way that the robot can do the same experiment with another robot, because of course you have exactly the same controller. It's entirely modular. Everything is modeled with a robot standard dynamics, and you can plug these components and create new controllers. Now, there's another thing that we can optimize, and apologize for this one. But I'll tell you the story. Is need to read it. You can these days parameterize everything about the robot. So the size, the masses, the length, everything that makes the body of the robot, and you can optimize also for the shape of the robot. So what we've done in those tasks where there's a collaborative weightlifting, we went also to optimize the size of the robot. And you say, okay, but the iCub is given size, you cannot change it. Sure, but we can design a new robot. That was the idea. And in fact, we then moved to optimizing that big functional that is takes into account all the parameters of the robot, still maintaining or having a humanoid with legs, arms, hands, etc., but going through an optimization that eventually will figure out the best possible robot. And the best possible robot was this one, slightly taller, slightly heavier iCub in a sense. Same technology. So joints are a bit bigger, but they're the same. The robot is not 30 kilos, became 65 kilos. You know, it's a bit taller. It's 140, if I'm not mistaken. So from the point of view of the optimal weightlifting, joint weightlifting with a person, this is what we obtain from the optimization process. Why not a larger one? Probably because given the constraints on the technology that we have, it wasn't doable. So it was out of the envelope of the possibilities given by the motors and the parameters that we set into the robot. Anyway, this is called ErgoCub, ergo from ergonomic iCub in a sense. And this is basically what we do in these days. You can see an older iCub and the new one walking here. And it's, I mean, just presentation of the robot is a grown-up version, not very, very different otherwise. What you can also see is that from this robot, we can now start building complicated behaviors. And these days, though, the complicated behaviors can also be learned. And now, the sensorized suit that we design comes to basically becomes the way you train the robot. And in fact, you can train from running teleoperation with the sensorized suit. So the same suit, the shoes that I mentioned, they're all data collections points or a means to actually collect data about what the person is doing. And if you teleoperate the robot, you can collect the same numbers from the robot. Therefore, you can have the person teaching the robot how to go through a task. And just since we're in the, let's say, in the time of deep learning, you can plug all these numbers into a big neural network, which is basically what we've done. Was far too easy to actually do it, in the sense that you just need a bit of GPUs and design a neural network that included here images, but also depth, but also movement. And in this case, there was also a speech interface. And the result is something like this one. These are experiments where the robot is doing stuff that was never programmed for. And so the saying hi is being generated just because during teleoperation, when the person was doing like this, the operator was extending the hand, shaking hands. Similarly, when someone was getting closer to a robot with a box, the robot will extend the arms to carry the weight. And when you do this, the robot will come closer to you. I think it's kind of fascinating because, I mean, it's very simple. And I mean, there's no guarantee that it works because we have so many cases where the robot just goes crazy. But it's interesting as a possibility because indeed with the sensorized suit and shoes, we have a great opportunity to just collect enormous amounts of data that can be plugged into the robot. That's it. I think as a summary, what I can say is that the social, under development, there are a few nice messages to be taken from that type of interaction. The physical is getting super interesting because it can be the way we create robots that can interact with us very naturally. And the two things combined, even better, although we haven't done it yet, but I think you can see the direction. This is, well, if I'm talking about the iCub, it was a lot of people that work on it. I mean, designing the robots, you can imagine the number of engineers that were needed. software and doing the experiments, and students working on the experiments and so forth. This is the group that was doing human-robot interaction, social human-robot interaction, and this is yet the other group that was doing the teleoperation system. So probably like 200 people overall. I mean, the project's been running for 20 years now, so there's a lot of people that came, graduated, moved on, and I can proudly say that we have managed to train good students that are now in also very nice universities from US, London. One of the guys is DeepMind, running a group doing robotics there. I mean, there's certainly plethora of opportunities, and I'm proud of the people that work with us on the iCub. Thank you.
Well, thank you very much for a very interesting talk. So we have like 15 minutes for questions. Do anyone have any question here? Any question?
Yes, Giorgio, I have a question about the experiment when you put the robot and the people put more attention to the robot. Maybe, well, that happens a lot because the people are surprised by the stuff that you are showing. How do you solve this? Maybe showing the robot before the experiment, or could you think?
Yeah, they're typically naive users. They never use the robot. We tell them a story. There's a bit of preparation for each experiment. The story is non-informative with respect to the experiment because they had to stay naive. But we tell them, oh, look, this is a robot. The robot is programmed to do certain things. You know, there's a creation of certain expectations that have to be managed well. It depends on the experiment. So for other experiments, they're very simple. It's more just measuring the reaction irrespective of the fact that they know the robot. We also run experiments with roboticists, and of course, completely different story because they used to work with the robots, and also the background knowledge on how a robot works is so strong that changes a bit the perception of the robot. Yeah, but indeed, it's part of the design of the experiments. Also, what you tell people before they go through the experiments itself.
Does the robot have any kind of world model, any kind of abstraction of its inputs?
Not really. If you're talking about the experiments where we doing more the autonomous behaviors on the robot, there's no world model in those. We have people, although we haven't integrated things, there are other groups that are working more on building full representations with, also the geometry of the environment being encoded into the system, but it's not yet part of what you saw here today.
Any other question here? I mean, en español pueden hacer, los traducimos.
I can answer in English even if the question is...
Eduardo, bueno, mi pregunta la voy a hacer en español porque no sé, me es más cómodo. Y mi pregunta es cómo los humanos podemos cuidar mejor a los robots para evitar como en un futuro un daño regresivo, no sé cómo decirlo.
For the time being, no risk whatsoever because the robot is it's far too simple. I mean, there's no risk. I think that the question is more. I don't think there's a danger per se for this. What the robot does is entirely under control, programmed. The question is more that they have many of those. And the day those robots can be deployed for certain applications. Is it correct to have the robots there, and what may be the impact in society of those robots? Currently, at least in Europe, we're extremely worried about the fact that we're going to have to maintain about probably 20 to 25% of people out of the working age. So it's going to be huge numbers, and there's not enough hands to actually help those people. So, I mean, applications of robotics for healthcare are really, mainstream in the research environment because we think there may be a need. Similarly, in factories, there's a lack of, manpower that is quite consistent, and people are going for, maybe we need efficiency generated through AI. Maybe we need robots to work on production, on manufacturing, and so forth. But that may be a situation where we may want to consider more the impact of robotics overall.
Any other question here or in the
Oh, wow.
When finding out the optimal robot configuration of the robot, when you show that it was being parameterized, what was the objective function? What method do you use?
That one was a genetic algorithm, although we switched to other systems at the moment. The latest development, we basically have the task, the environment, and the robot modeled as differentiable models so that we can basically run a gradient descent on that model. The parameters there, the objective function was the robot that minimizes the muscle skeletal stresses on the person on a task of joint weight lifting. So that was for that specific case. But I must say that it was a kind of an early attempt, and the new stuff is very powerful because you can use libraries, I don't know, JAX or libraries that allow you to design entire environments that are completely differentiable. So you can do gradient descent on those, including the entire model of the robot. So that's basically where we're going. It's huge simulations, but it gives concrete hints on how to design the robot next.
I think I have some questions online. One of the questions is, in sort of the short time, can robots be able to act as seen on many Hollywood films, mainly when it involves the use of AI? It's possible to.
Yeah, I mean, not necessarily. I mean, if you talk, it's kind of interesting, but if you talk to people, you've seen the Boston Dynamics videos recently, no? I mean, beautiful and moving incredibly well. And there's not much AI there in the controllers. Actually, Mark Ryder used to say, this is just good engineering, make it work. So it depends on what you expect to see from the robots. If you expect to see a robot that interacts and speaks to you, yeah, probably the new large language models are needed for that. But for everything else, I don't know. It's a mixture, I would say. Engineering, better neural networks, and combining the two things is probably, at least at the moment, the way we will go.
Thank you. Here, another.
In your opinion, why do we try so hard to create human-like robots? And I think about it because at the ADS case, would it be the same performance if the robot didn't seem so much like a human?
I think, why we do it, I think there's a question of fascination for human form, and we find it challenging to design something that behaves like us. On a more rational basis, there's a reason for if you need machines to work in the environment that has been designed for us, it's good to have hands. It's good to be able to walk, to climb stairs, to open doors, to use tools. So it's very our entire world has been designed by us for us, and if we want machines to use this world, these tools, it's good to have a humanoid shape. That's a more of a reason. There are other reasons. Rodney Brooks used to say that if you want to design human-like intelligence, you need a human body. So that intelligence will only develop and learn like us because he's controlling a human body in a sense. And this may be, it's not too far from the truth, at least. Neuroscience is also finding a lot of the connection between perception and motion in our bodies is so much dependent on the structure of our body. So there may be a deeper reason why we like to develop human robots.
Here in the chat we have some interesting question. There is a way to have access to one of your robots here in Mexico.
There's not, but there's. I mean, we never built a robot for a Mexican university. I mean, it's theoretically possible, but in practice, it didn't happen. So.
And also, the person asking for your contact.
Okay, sure. I mean, I'm happy to share the contact. Yeah.
Okay,
yeah.
Thank you.
I think if you look for my name, you should find on page of the Institute, and there's a form to send me an email.
We still have time for any other questions.
Well, I wanted to ask if there have been any studies that have studied, well, how different cohorts, different age cohorts interact with robots. For example, as you said, we have a population crisis because a lot of people are getting older, and we need health robots. So, for example, for people who might not have grown up with tech, like my grandparents, how's that going to work? Is that going to be like, have there been studies about how we can make these robots more approachable to those kinds of people?
I mean, the stuff we're doing in human-robot interaction goes in the direction of not requiring any, you don't have to understand the technology very deeply. We're not there yet. So as you can imagine, I mean, the robots are still cranky. There's still complexity in using a machine like that one. But I mean, the idea is that eventually you'll be able to teach the robot a new task just by showing the task. That's a paradigm that we're developing. So now we're doing it with teleoperation, which is complicated, but one day it's probably this visual demonstration will be enough to teach a new task to a robot.
Here in the chat, someone asked about if you think that culture or age, or in general, I think some social aspects of the persons, the robot interact, can you influence the task or the solution of the task?
Probably yes. I would say that especially for a robot that is designed to interact with a person and then starts learning from the person, will probably develop a very specialized way of solving tasks and be maximally of support of that person. So I don't know. I think it's a nice, fascinating topic of, maybe one day we'll be selling robots that are all the same when they go out of the factory, and then they develop personalities because of interaction with people.
Well, any other question here, Antonio? Yeah.
Again. You said that the robot has some problems with learning through vision, but not through motion capture.
Yeah.
Because that means that with this, again, implementation of the world model and self-representation of the embodiment, it could try to process the world into perceiving and understanding others' actions and understanding it just as well as a motion capture.
It's all plausible that we go to something like that. For now, it was a lot easier to use the teleoperation as a way to guide the robot through a task. And therefore, we went to the easiest, but it's to be foreseen that at a certain point you can have just a robot standing there looking at a set of actions or a task being performed by a person, inferring the movements and then building the complete sequence autonomously. I think it's plausible. It's not too far actually because you can build a model like that. I mean, a visual motor model can become part of one of the neural networks that we're designing these days.
Thank you. We think we can move to the next presentation. Thank you very much.
Thank you.
For your
Thank
talk.
you.
And there's a. Thank you very much.